Welcome back to Mathematics Lifeline. In today's video, I want to show you a problem that I saw actually on a math clock. We found a solution for it. It works out pretty well. And the solution actually uses what's known as the Basel problem. So I'll talk about that a little bit in this video. And if you have any other solutions to this, then I'd love to see them. I'd love to hear about them. This was the first thing that we thought of when we were solving it. So first, let's talk about the Basel problem. The Basel problem, it's about finding the sum from k equals 1 to infinity of 1 over k squared. So we know that this converges because it is a p-series, so it's going to be a convergent p-series, but what is the actual numerical value? It turns out that the numerical value is pi squared over 6. So this was actually solved by Euler originally, and it's called the Basel problem. The proof is pretty complicated, so if you're interested in that, then I'll write it down so you can look it up. It's called the Basel problem. I won't go into that proof in this video, but we can actually use this. If we use it as a fact, we can definitely show that this fraction is equal to 8. So let's go ahead and get started. If you want to try, feel free to pause the video, and I'll go ahead and get started right when you come back. So the solution that we came up with involved looking at the even and odd numbers of these series. So if we look at this sum that's in the denominator here, this is by definition all of the reciprocals of odd numbers squared. Because 2k plus 1 is the definition of an odd number, right? No matter what integer value of k I plug in, I get an odd number out. So when I write this down, the first few terms of this series are 1 over 1 plus 1 over 9 plus 1 over 25 plus 1 over 49 plus ... Right? These are all the odd number reciprocals squared. And again, this is just from plugging in values of k. So if I plug in 0, I get this one. If I plug in 1, I get this one. Right? So I keep going down the line. Now, the Basel problem isn't restricted to just odd numbers. It's restricted to every integer. So it really isn't restricted. So if we want to figure out something and compare it to the Basel problem, we need to also look at the sum of all the reciprocals of even numbers squared. So let's think about how we can write that out. So if we want to look at even numbers, well, let's use the definition of an even number. So we'll need to start from 1 in this case. But we'll have 1 over 2k squared. Because if I plug in any integer value k, when I do 2k, it's going to be even. So this is just like the last one, except we're restricted to even numbers. So when I write out the first few terms of this, I'm going to get 1 over 4 plus 1 over 16 plus 1 over 36 plus, and I would keep going. So again, plug in 1 and I'll end up getting 1 over 4. If I plug in 2, I'll get 1 over 16 and so on. But the reason that we do this, it may feel kind of useless right now, but we want to eventually compare this to some numerical value that we know, and that's where the Basel problem comes in. Because if we look at this sum, so the sum from k equals 1 to infinity, 1 over k squared, well, let's write out the first few terms of that one as well. So if I plug in 1, I'm going to get 1 over 1, which I know these simplify, but we're going to leave it like that for now. Then I get plus 1 over 4, plus 1 over 9, plus 1 over 16, 1 over 25, and so on, right? So it's all of the any integer reciprocal squared. So 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, right? This is all those terms. But if you notice, with these two series that we've created, we have every single term in this series, right? We have 1 over 1 right here, 1 over 4, 1 over 9, 1 over 16, 1 over 25, and if we kept going, we'd get 1 over 36, 1 over 49, and it would match it forever. So that tells us that this sum, the sum of the Basel problem, is equal to these two sums added together. So since we know that the Basel problem, its sum is pi squared over 6, we can say that pi squared over 6 is equal to the sum from k equals 1 to infinity of 1 over 2k squared plus the other sum that we're looking for. K equals 0 to infinity, 1 over 2k plus 1 squared. We can definitely say this, again, because if we look at all the terms of this series, remember this is the same thing as pi over 6. If we look at all the terms, they match adding up these two. So the goal is, we're not going to be able to easily get the numerical value of this series, the one right here, but we can actually get this into a form of the Basel problem, which is why this is so helpful for this question. Because if we look at, so let's write it here, the sum, k equals 1 to infinity, 1 over 2k squared. If I just square this denominator, I'm going to get the sum from k equals, 1 to infinity of 1 over 4k squared. And I can actually factor a 1/4 out of that. So I get equals to, 1/4 out here times the sum, k equals 1 to infinity of 1 over k squared. And now you may be able to see why this is so helpful, because this sum is the Basel problem again. So it comes into play yet again. And we know it's 1/4 of that sum's value. So this is equal to 1/4 times pi squared over 6. And when you multiply that out, you get pi squared over 24. So we now know that the numerical value for this one is pi squared over 24, which means to get the numerical value of this series over here, all we have to do is subtract the pi squared over 24 to the other side. So we have that pi squared, let's keep this separate, pi squared over 6 is equal to pi squared over 24 plus that sum. And then now, again, to solve for that numerical value, all we need to do is just subtract pi squared over 24 to both sides. And when you do that, you'll find that the sum that we're looking for, from k equals 0 to infinity, 1 over 2k plus 1 squared, is equal to pi squared over 8. Right? When we subtract those, we'll end up getting pi squared over 8. So knowing that, we can show that this is equal to 8 because we have pi squared over, we know this sum evaluated to pi squared over 8. So this is equal to pi squared over 1 times 8 over pi squared. These will cancel and we get 8. So we've shown that it's equal and that the clock is correct. So yeah, I think it's really interesting to compare it this way. It's a less algebraic approach and more of a kind of a logical approach, right? We saw that this sum that we were looking for was the reciprocal of the odd number squared. So why don't we just compare it to the reciprocal of any number squared? And to do that, we need the even numbers, which can end up working out to be a form of the Basel problem. And that gives us our answer right off the rip. So yeah, I think this is a super cool question. One of the more complicated ones I had seen on a math clock. The one that we got is pretty complicated in every aspect of it. So you may be able to even look it up. If you see, I don't know what it's called, but if you see the question, then you can maybe try solving the other ones. But yeah, hopefully you enjoyed this video. It's just a little bonus question. It has nothing to do with really any coursework. It's just a fun little question to do. So hopefully you enjoyed. Again, if you have a solution, let me know. I'd love to look at it. I'd love to talk to you about it. If you have any questions, again, let me know. I'll try to answer those to the best of my ability. But if not, then I will see you in the next video. Thanks for watching.